resume. So, simple question, screen visible, voice audible.
Yes, sir.
Great. So I would suggest that you look at the representation theory by Afkin, I mean in the book Afkin, and I will still upload certain pages from some other book. Those who will be interested in knowing, I will of course tell the name as well. But I will also upload something from there because it is not written in the explicit manner in which I am going to explain the things today. Fine. Okay, what we were doing. We say that after finishing first part of our group theory, we basically finished at the point where we discussed about homomorphism, which is nothing but a mapping from one group to another group. So representation theory, representation is nothing but a group homomorphism, that is, it is a mapping, where we are mapping a group into the invertible linear operators on linear vector space. So that's the idea. Now, why this idea will become very useful? This idea becomes useful because we know that these linear operators will be represented by matrices in a given basis. So once the basis is given, then an operator is represented by matrices. So when we are saying representation theory, that means that representation is a group homomorphism, which in finite linear vector spaces basically maps us from any group to a group of matrices. So that's the idea basically behind it. So in several books you will find representation theory is nothing but group being mapped to matrices under matrix multiplication. In other books which generally deals with physics, they will surely mention that it is basically mapping into the linear operators, which in the case of linear vector space becomes, which in the case of finite basis becomes matrices. Okay, and then we of course discuss that since it's a homomorphism, so the property of the homomorphism dg1 into g2 should be equal to dg1 into dg2. Remember, when it becomes matrices, it is the matrix multiplication which now comes into the picture. Yeah, so and identity element gets mapped to identity, inverses gets mapped to inverses. Those are the regular things about the homomorphism, and that is why I generally write the word group homomorphism and not only mapping. It's not a generic, it is a homomorphism. Okay, so what do I want to do in today's class? In today's class, I will try to show you that there exist many representations for a given group. So even if a group has only few elements, then also it can be represented by many different kind of structures. And what are those structures will be nothing but the representations. Since we were discussing yesterday how to think about the group, and we discussed about something called parity, and since you also answered certain questions related with parity, I thought let me just take this parity operator or the parity operation. Now, parity operator is such that if I am applying this parity operator, let's say P, on some X, then what will be the result of this? This will become
minus x.
minus X. And we also discussed if we apply P, which is nothing but P square on X, then this will be
X.
this will be equal to X. So that means that it is an idempotent, and P square, okay, is nothing but an identity operator. And this gives us an idea of constructing a group, let's say with two operators. So one is an identity operator, which is generally is E, and another is this, such that we have this, and that's the starting point. And we are going to show that there exist several representations, how these representations are interpreted, etc. Those are the rest of the points in this. So we will start with this. Now, in order to show that there exist many representations, let's now think about several cases. Let's consider a very simple case that there exist functions. So functions in the linear vector space, for example, there exist functions, let's say of the kind only phi x, which is nothing but even functions. So there exists a space of even functions. What's the property of the even functions? That phi1 of minus x will be equal to phi1x. That is how an even function is defined, which is with respect to, let's say, x equal to 0, it is symmetric. Yeah. Now, Let's think what each of this operator is doing on this function, because operators generally operate on the function. So let's say our E operator operates on this phi 1x. So what does this give?
Phi 1x.
So this
Phi
gives
1x.
phi 1x. Excellent. And what will be this P operator if this guy is going to work on this? So okay, let me just write. Then it is going to give. So this is going to do it phi 1 minus x, but then phi 1 minus x will be
Why? Why? Why?
phi 1x. Now look into this interesting feature. This phi 1x, this guy or set of even functions, they are nothing but the eigenfunctions of both E operator as well as P operator. So I can construct a basis consisting only of my even functions there, such that the eigenvalues here turns out to be both plus 1. So now at this point, I'm just going to write something and then going to describe it. So I can think about making a representation, which I will call as my first representation, in which d1 is nothing but plus 1, which is nothing but the eigenvalue of, and what will be d1p, eigenvalue of p operator?
1.
That is also plus 1. So, and remember that 1 and 1, even though they look as numbers, but for me, if I am talking about the matrices, what kind of matrices they are? What is the dimension of these matrices? It is 1 cross 1 matrices, which is nothing but numbers. So suddenly, interestingly, what I have done, if I construct a space of even functions, or if I consider space of even functions, then my group I and P, they get mapped to two element, which is D1E and D1P, and I call this my first representation, which is actually a very trivial representation, that both the elements get mapped to only one element, right? Is it a group homomorphism or is it a group isomorphism?
ISO.
Homomorphism.
When is it isomorphism? When both the elements get mapped to a single element. So it is a kind of 2 to 1 mapping. Remember, both I and P, that gets mapped to plus 1. It is a group homomorphism, right? So we have actually constructed just like that. We have constructed our first representation, and I call that representation A1, where I get the mapping of I and P into two numbers, one which is nothing one or single one, under multiplication of numbers. So I can now just define that if my space consists only of the even functions. Okay, so let me just continue. I mean, this is not the only possible space here. I can also have many other spaces. Case 2. Let's say there exist phi to x functions which are only odd. Now, what is the property of the phi to x functions if they are odd? So what will be phi 2 minus x?
Minus phi 2x.
Minus phi 2x. So let's see what our operator does to these kind of functions. So let's say E operator operates on phi 2x. What does this give? Phi 2x, right? What about P operator? Okay, capital P operator, since I'm writing, acting on phi 2x. This will give phi 2 minus x, which will result in
Minus 5 to x.
minus phi 2x. Aha, so we are now talking about space of odd functions, and this has given us another representation. What representation is this? Now let's just look into it. I call it D2, and this representation is D2E is equal to eigenvalue of the first E operator
1.
plus 1. And what about the eigenvalue of the P operator?
Minus 1.
Minus 1.
minus 1, suddenly you will see that in this representation, my group is represented by these two elements. Okay, I should write group and D2P. Okay, you can even write down the operators where first one is plus 1, second is minus 1. Again, what will be the dimension of the representation? First,
1 by 1.
since it's number is 1 cross 1 and we call that dimension 1. Remember, we have to have only square matrices, so dimension is just given by single number here. So dimension of the representation is 1. Is it isomorphic or is it homomorphic? Is it group homomorphism or is it group isomorphism?
Isomorphism, sir.
Sir, isomorphism.
Isomorphism, sir.
Isomorphism. Okay, so it's a good way to write group isomorphism or group homomorphism. It is just, but what happens? Suddenly you have got two representations of the operator E and P in the space of even functions, in the space of odd functions. But why should I limit myself to this? I can also have some other things. So let me just go to case 3. Now let's consider function phi x, where we cannot say that this is even or odd. Now what will happen? Now what will happen? If I am going to apply E operator on this phi x, what is this happening?
So we get 5x.
Great, this guy is simple. If I am going to apply P on phi x, what we are going to get?
So I can't say.
No, can't say no. You will say it is phi minus x. Remember, it is the P operator, right?
Yes, sir. Yes.
But you cannot do further. Now, this space has a problem in the sense that you cannot take phi x to be just the eigenfunction. Yeah, this space does not have that. If I want to now consider space of functions or basis functions for this space, I will have to include functions of this kind and I will also have to include function of this kind. Only then you will have all the cases cleared. So what do I mean to say? I mean to say that any basis function which we are going to build, which earlier one were only phi 1x, that is even functions, or only odd, that was phi 2x. In this case, the two operators E and P won't have simultaneous eigenfunctions. So you have to have at least two of the functions in this basis. So only if you have these two functions in the basis, then you will be able to write any general function in this space in terms of these two ones. So this is basically coming directly from my quantum mechanics knowledge. But now that I have got this knowledge that my basis function is no longer a single function, however, it is the two functions which will form basis. So I will have to do what? I will have to see the effect of operator E on both the functions and construct a representation. And I have to see the effect of P operator on both the functions and see what happens. And that's what we are going to do next in order to construct this representation. So let's just try to do something. E operator. So anyway, by the way, even before proceeding, if a basis function has two vectors, what will be the matrix representation of E in terms of dimension? So operator in a basis in which there are two functions will be 2 cross 2, right? I mean, that you already know. But let's just see whether you can write down the matrix. So E of phi x, you have already written phi x. And I am going to write it in an interesting way. Please look into it. I of phi x plus 1 of phi x, so this is number 1, and 0 of phi minus x. Remember, this is how we try to write down a general vector in terms of the basis vectors. That is how we used to do that. What will be the case E of phi minus x? This will be Phi of minus x.
minus x.
So how can you write down now? Expand it.
0 phi x plus 1 phi minus x.
0 phi x plus 1 phi minus x. Now, can you give me my third representation of E, which is nothing but a matrix 2 cross 2?
1 0 0 1.
Okay, 1 0, but please see the way I always do it is this first column is this. I see that in many of the cases where you are doing your exam problem, you are not doing it like this. I do not know from where you are taking it, but please see it is the first column which represents the first row of my one, and it is the second column which represents the second row. So even though it looks like, I mean, they are both zero and hence ultimately it doesn't matter here, but in general be careful in that notation. If not careful, then at least be consistent. So new representation of the same operator E and P. I have this third representation in which this operator is represented by 2 cross 2 identity matrix. So dimension here is 2. Let's just try to do the same thing for P. So P operator acting on phi x. What does this give?
Phi of minus x.
Phi of minus x, which can be written in terms of those basis functions.
0 phi x plus
0 phi
1
x and 1 phi
0
minus
of
x.
phi x plus 1 of phi minus x. Excellent. What about this P of phi minus x?
phi
Sir,
of
1 of
x.
phi x and 0 of phi minus x.
Right. This will be 1 of phi x plus 0 of phi minus x. And that means in this representation, D3P, which will be written as first
0 1
column.
0 1
Okay,
0
I mean,
1.
doesn't
0
matter.
1 0.
0. It's a non-diagonal matrix. Of course, it has only off-diagonal ones, but it is now 2 cross 2, and this I will term as my third representation, A3, which will have two components. Again, matrices basically, since we have chosen finite basis. Okay, these are operators. Okay, just remember that. But anyway, so what I have got in essence, let me just summarize and then I will let you ask question. So I basically started with a group of operators where I discuss two operators, and I know that two operators having this p square equal to e will form a group. Now this operator in the representation, if there are even functions, which means only phi 1 x, the basis function is only a single function. What does that mean? That phi 1 x is the simultaneous eigenfunction of both e and p. And we get our first representation A1, where the group is represented by just one number 1. We call it a trivial representation. Then we said, okay, in this space of odd functions, I have this phi 2x, which is basically, again, the phi 2x, since this being odd, was the simultaneous eigenfunction of both E and P, and I have my second representation coming up from this. Here the group is represented by +1 and -1, where identity of course is mapped to +1. And then I said, okay, if I have a general function, there I need to have in the basis at least two functions. And from there I can build my third representation, and the third representation will have two matrices, 1 1 0 0, which is an identity matrix, 0 1 1 0, which is another one. So this guy, if you look into it, we have D1E, D1P, both of them map to 1. Next one we have D2E, D2P, and the third one I already have D3E and D3P. So I already come up with a summary that there can exist many representations for a given group. Point 1. Representations are not unique. In certain cases, we had homomorphism, and in other cases, we had isomorphism. Can you tell me which one is the homomorphism and which one is the isomorphism? A1, is it homomorphism or isomorphism? This is
Homomorphism.
homomorphism, right? Very good. What about A2 and A3?
Isomorphism.
Both of them are isomorphism. That just means that, of course, group homomorphism is there, but the mapping is also bijective. Let's do something else. Dimensions. What about the dimension of A1 and dimension of A2?
1.
That is 1.
One.
What about the dimension of A3?
2.
2.
2. So that means that representations are not unique when we are saying there can exist the homomorphic representations or the isomorphic representations. There can exist difference in the dimensions as well. So when I'm saying not unique, it is in terms of both the homomorphism and the isomorphism, as well as in terms of the dimensions, that representations are not unique. In fact, you know that you can find out infinite bases, and hence you can say that there will be infinite representations anyway. But here the point is even bigger. We have dimension 1 representation, dimension 2 representation, and we can continue to build representations on the basis of that. And I am going to do as the next one. But at this point, I am compelled to give you a definition of something what is called faithful representation. And the definition is that the faithful representations are nothing but the isomorphic representations. So can somebody tell me, out of the representation A1, A2 and A3, which of the representation of this operator EP is faithful?
A2 and A3.
823.
So A2 and A3. So even the faithful representation does not need to be unique. Okay, so that's interesting. See, even though representation theory, it is going to help us because we are going to multiply matrices. But now we are facing a problem that there can be so many representations representing same set of group. Questions I will invite at this point before I go to the next point.
Two questions, sir.
Yes.
Sir,
So first question is that how just
Okay.
so how A1, A2 and A3 are A1 is homomorphism and A2 and A3 are isomorphism.
Okay, that you will have to just remember from my homomorphism and isomorphism lecture, but I can just tell you here, I did mention when we were doing the group homomorphism and isomorphism, if there exists two element in the group, yeah, so there were two element in the group with P square E. Now, if there exists two element in the group, then the group isomorphism will be such that there will be exactly two distinct elements in the new group. So see, in the first one, D1E and D1P turns out to be same number. So they are not distinct elements, and hence there is only one unique element in the first case. So that means that two of these E and P gets mapped to only one element plus one in first representation A1. And hence
Got it.
it is group homomorphism. Whereas in the next two cases, yeah, okay, good.
Thank you, sir.
And the second question?
Sir, it is clear now. So I was asking about the dimensions. It is clear.
Okay,
Thank you, sir.
dimension is coming from the matrices dimension. Remember,
Yes.
number is nothing but dimension 1. Okay,
Yes.
now when I say matrix multiplication need not be commutative, AB is not equal to BA. But if the dimension is 1, then what will you say about the matrices?
Commutative.
It is mandatorily commutative, right? I mean, numbers are always commutative in terms of multiplication. 1 cross 5 is equal to 5 cross 1. It is the higher dimension matrices which may or may not be commutative. Yeah, okay. So let's just go to the next point. Now
Sir?
that yes.
Sir, why do we call them faithful representation?
Oh, faithful is something like that there were two and there are exactly two. So if you want to reconstruct back your E and P out of your representation, you will reconstruct, yes, that there exist only two elements in a group. If it is not a faithful one, then you cannot figure out how many how many members were there in the original group, and hence you are not faithful to your original group, right?
Okay, sir.
I mean, just by looking at one, can you say it is coming from 2 or 3 or 4 member group?
No, sir.
Yeah, so that is the faithful part of it. It is faithfully ensuring the structure of the group. I mean, you can say that. Okay. Okay. Yeah, let's just do something now further. Now that there exist so many groups, what else can be there? Okay, let's just discuss. I did discuss that if there exist basis functions, yeah, so let's say I have basis. And in this case, I mean, in this example, we had, let's say, 2. Interestingly, our basis functions were orthonormal. I mean, I wouldn't say how it is, but phi x and phi minus x are orthogonal. Either the function is phi x or the function is minus x. I'm not going into that detail right now, but let's say there exists basis. I can always do this guy. S9 and then chi I, which is new basis for this, right? Using a matrix which is called, what kind of matrix changes from one basis to another in the same linear?
Transformation matrix.
The transformation matrix.
Right, transformation matrix or change of basis matrix S to P, S to S prime. In fact, once we know that, we also know that if I want to write down my operator in new basis, then how can I write down using this transformation matrix?
P inverse TP.
P inverse TSP. I mean, you cannot forget that. Okay, so doesn't matter. Similarity transformation, this is what we defined. And we said that this T in S prime is, even though matrix wise, it looks very different from TS, but for all practical purposes, they are similar matrices. Why? Because they have the same eigenvalues, they have the same traces, they have the same determinants. So similarity transformation results in going from one matrix representation to another. In fact, if you build the similarity transformation in a particular way, then you can even diagonalize the matrix using this one, right? Yes?
Yes, sir.
Right. So that means, that itself means that even if I am going to a 2 matrix, that is there exists only 2 by 2 matrices, then within the same dimension, that is dimension 2, because the basis has 2 vectors. Now, within the same basis or within the same dimension, there can be many representations of the original group. So we have already seen that there exists one representation in which the 2 matrices are there, 1 0 0 1 identity and then 0 1 1 0, which is non-identity, it's off diagonal one. So that means that there can exist further representations which can have exactly 2 elements, and both of them are 2 into 2 matrices using your similarity transformation, right? So let's just see if we can build this similarity transformation in this case. Okay, so let's do this. Now what I'm going to do, we had originally phi x and phi minus x. I will take it to a representation where we have phi ax and phi bx. So this is my, sorry, 4. And where phi ax is defined as 1 over root phi x plus phi of minus x, and phi bx is defined as 1 over root 2. Can you think of what have I done? What kind of phi ax and phi bx are these guys, even though you did not know anything about phi x and phi minus x?
Sir, even and odd.
Normalized
Right.
eigenstate.
Yeah, this is normalized, but the important point is that if you are going to find out phi a of minus x, then what will be the result?
So phi
Phi
a of x.
x.
This will be phi a of x. Just do that minus x everywhere and you will see the same structure will come. What about phi b of minus x?
Minus of phi b.
Minus
of x.
minus of phi b of x. Minus, that means phi b is an odd function. So all I have done that writing it in terms of the generic functions basis, instead of doing that s, I just took it to s prime, which is made out of the even and odd functions. Now can I write my p transformation matrix for this guy? I have normalized it.
1
Yes.
by root 2, 1 by root 2, and
1 by
1
root
by root
2
2
and
minus
1
1
by
by
root 2 for the first column, which is coming from here, and then 1 over root 2 minus
minus
1 over root 2, which is coming from the second one. Yeah, or I can simply write it down as 1 over root 2, 1, 1, 1 minus 1. Right. Now, please find P inverse for me. So now that you have found P, please find P inverse.
Minus 1 over root 2 into 1, 1, 1 minus 1.
1, 1, 1 minus 1, and then minus 1 over root 2. There is a small problem there, although. So 1 over determinant, right? 1 over determinant. So you have 1 over root 2 minus 1 over root 2 and 1 over root 2, 1 over root 2. What is the determinant of this guy?
Minus
1.
No, it won't be
Minus
1. It
1.
will be
Minus
minus 1
1.
over 2
2 root 2.
minus 1 over 2. So this is this one. No, not 2 root 2. It is a simple one. You see, 1 by root 2 multiplied by minus 1 over root 2. It will give you minus 1 over 2. Minus of again minus 1 over 2. So this will just give you actually minus 1, nothing beyond that. And what will happen to the elements? This will be diagonal elements will just be
minus 1,
interchanged
1, minus 1,
and
minus 1.
right. So this will become the case, and hence this guy will become exactly what? 1, 1, 1 minus 1. In fact, in this case, it becomes rather simple. There is something.
Son 1 by root 2.
Where is 1 by root 2 should be coming?
Son numerator.
And why it will come?
Sir,
Why it will come? Because each of this guy was this.
1 by root 2.
Each of this guy was there. I am just writing it because I know plenty of you, I mean, somehow while doing this, do not take care of this 1 over root 2 factor appropriately when you just take it outside. Anyway, let's just write down 1 over root 2. This will turn out to be a simple one. I mean, it will turn out to be exactly P if you just go back and look into it. So let's diagonalize. Let's diagonalize and then get our A4 representation. We have two matrices, remember, D3E and D3P. And by the way, I haven't said it explicitly. Every time you are seeing this superscript, it is just another representation. So D3P is the second matrix in the representation A3. Yeah. So in this case, now we should be talking about D3P and D3 P, both of them do this. So do this of them. That means first D4E P inverse, okay, P inverse D3E times P. What will be this? This guy is just an identity matrix. P inverse identity P. It will become P inverse P, which is nothing but identity matrix, right? So D4E is basically turning out to be same as D3. So that is not going to diagonalize. I mean, this is already a diagonalized matrix. So what else will you do? What about this D4P? Okay, now I will have my problems. And I will discuss about the problem later. But okay, I'll still write it. D3P. So here you will have to do some calculations. 1 over root 2, 1, 1, 1 minus 1. What was D3P? 0, 1, 1, 0. And what is the next one? Again, 1, 1, 1 and minus 1. It is same as this one and 1 by root 2. So please do this matrix multiplication and give me the result. And I will tell you my problem later.
Sir, 1 0 0 minus 1.
1 0 0 minus 1. Okay, let me see.
Yes, sir. Correct.
Yes, sir,
That turns
same.
out to be correct one. Okay, so that means you have got new representation in dimension 2. What is that representation is here? A4 is going to give you D4E and D4P. Okay, I should now continue to apply this operator signal, which is nothing but, okay, this guy, okay, 1 0 0 minus 1. Wow, this is dimension 2 isomorphic representation of a the same group. So what we have done is basically we have converted our A3 to A4. Why I have done it, I am just going to come next to it. However, first, the problem which I am mentioning that is coming in the notation, my matrix name is P and my operator is P. So P and P are getting confused now. So after I have this guy coming in, please see that whenever I am going to use my operator P, I am going to put one caret sign on top of that so that you can make a distinction. You got the problem? I mean, in principle, it is not a problem, but those who are going to look only at the notes, they will have this issue which will be coming up. That okay, these P are getting confused. Which P is the transformation and which P is the operator? But I hope I made my question, my problem clear to you guys. Is it?
Yes. Yes, sir.
Yeah,
These
it's the same
errors should be
notation.
there, sir.
So I should have P versus P. What's this? P versus P. Okay. Some extra universe, multi-universe system. Anyway, let's just come back, which is a rather interesting one. So I have got A4, which is the next representation, and this representation I got from my P inverse A3P. Now I did give you, to be honest, I did give you the transformation matrix. But let me raise a question at this point. If I do not give you transformation matrix, would you have still found your P from your D3? I mean A3 representation. What was the A3 representation? Let's go back. This was this. Just by looking at A3 matrices, can you just tell me, would you still have found the representation A4 if I did not give you the change of basis? Question part 4, question 1, I guess. Diagonalize a matrix. How are you diagonalizing the matrices when I was not giving you the change of basis?
Eigenvalues,
Calculated the
eigenvectors,
eigenvalues and
integrating
eigenstates.
All you
vectors.
were doing was the finding the eigenvalues. And can you just quickly tell me what are the eigenvalues of this D3P operator? Okay, I mean, I should write. Can you quickly tell me what is the eigenvalue of these guys? This guy, eigenvalue?
One.
So plus or minus 1.
Plus minus 1. So if you diagonalize this matrix, what will be the diagonalized matrix structure?
1 0 0 minus 1.
So that means the diagonal elements will be 1 and minus 1, right? Now look at what we have got in our A4. 1 0 0 minus 1. If you diagonalize your identity matrix, it will remain same. But if you diagonalize any other matrix, you are seeing that I would have got the same result if you would have diagonalized your second matrix. Diagonalized in the manner in which. So I showed you the reason for diagonalization because I am basically going from any random function spaces to even and odd function space. But you would have got this result even if you go just by the matrix way. So now that you have got it, there is something very interesting. And let me say what is very interesting about this. Look at the structure of these two matrices D4E and D4P. Okay. And look at the structure what I got for my D1E, which was the even function, space and odd function space. Operators, come guys. So what were these values? Just remind me quickly. D1E plus 1, right? D1P
+1.
plus 1, excellent. D2E
Plus
1.
plus
1.
1, right? D2P
minus
-1.
minus 1. So let's just look into this D4E. I can write down my D4E operator. Look carefully as D1, sorry, not this, D1E 0, 0 and D2E, and I can write my D4P, and I will tell you what am I doing. D1 E 0, 0 and sorry. So something what I have done, let's just look into it. I got my first representation D1E, which turned out to be just number 1. Yeah. In the second representation also, which was odd function representation, my D2E was +1. So I just wrote D2E here. Yeah. And now correspondingly in the D4P structure, which is my fourth representation, I have D1P, which is +1, and that is coming from the even function. And then D2P, which is coming from the odd function I have written here. In fact, this looks like that I can write down this as something interesting. Okay, this guy has to help me. This is a plus symbol. My document is getting saved. Erase everything so that I don't make a mess here. Come back. Plus this guy D2E, and this guy I am writing as D1P, okay, operators, plus D2P. What I have done is I am breaking down my representation which we got in A4 as the some sort of sum of the original representations which I get D1E and D2E. And I can do it consistently for both the elements. It's not only for one element, it is for both the elements. In fact, I can write my A4 as nothing but A1 and A2. So it is almost as if A1 and A2 were some fundamental representations, and any representation which I build, let's say A3, if I diagonalize that representation using my similarity transformation, I can break it down to some representations which is simpler. So at this point, I am invoking a concept of what is called reducible representation. A reducible representation is the one which can be diagonalized so that it can be written in terms of some other representations. And those other representations in which we are writing it, they are called irreducible representations. So I'm going to, of course, say a few words on that again, but at this point, I will just invite questions so that you ask questions on what I have written.
So D1 and D2 are fundamental representations, right?
Yes, at this point, yes. I mean, fundamental in the sense D1 is the non-fundamental representation. I mean, this is not a fundamental. This guy is a fundamental one, but both are irreducible. I mean, you cannot reduce the numbers to something even more fundamental matrix. So higher dimension matrices are written in terms of the lower dimension matrices, but numbers are the lowest dimension matrices which are possible. So
Yes,
when
sir.
I am saying A1 and A2 are some sort of representations which cannot be further broken up, they are called irreducible. Now you cannot reduce it further. Yeah. So A1 is a fundamental representation. No. A1 is an irreducible representation. Yes. A2 is a fundamental representation. Yes. A2 is an irreducible representation, yes. But the point is bigger. Let's not worry about the fundamental for the time being. A representation of the higher dimension can be written in terms of the representation of the lower dimension, such that the numbers, if you get at the end, then they are called the irreducible representation. So what we say that the higher dimension representations can be written as some sort of a sum of the lower dimension representation. This is what we call as the reducible representation gets reduced to irreducible representation. Why this is important? Remember, I did say in the beginning that we can have many representations. Now, when you have many representations, what to do out of those? There are so many of those. Now, this reducible and irreducible representation is giving you an idea that you do not need to worry about higher dimensions representations. They can always be constructed out of your irreducible representations. So you have got some sort of a building blocks, and this kind of sum which I have written, which I have basically encircled, this is called direct sum of representation.
So
Ready?
why can't I call irreducible representation unique one, as they can't be broken in further because they are the
Why
lowest?
can't I say irreducible representation
Unique,
as
unique, sir, unique representation.
unique representations? Okay, I mean the word, it's not about the, okay, let's just say it like this. It cannot be further broken down. That's the quality, right?
Yes, right,
Yeah.
sir.
So that's the quality which you are using here. It's not about, I mean, you can say that they are unique. Of course, each one of those are looking like to be unique. Somehow the higher order ones, the uniqueness, even though it is there in terms of the representation, there is nothing wrong. If you use A4, the two matrices like this, they are looking like this, but they can be such that they can be written in terms of the smaller ones. Now, I do not want to leave you guys here because I just want to give examples and then leave you guys because it is just in the continuity. So let me just finish it off by giving you examples, and you yourself will see the importance of the irreducible representation. Let's say that I am still not exhausted with the representation. I want to go for higher order representations further. So 3 by 3 matrices, 4 by 4 matrices. So if I give you a space of functions, let's say phi, not phi1 I have already used, psi1x, psi2x, psi3x, and all of these psi's are even. Can you give me the representation, let's say d5 of E and d5 of P directly without doing any calculations? Remembering that you already got your irreducible representation. So a space of functions, all of them being even. What will be first entry?
So 1.
So D1E, which is nothing but +1, right? This is 1, right?
Yes, sir.
0, 0, I do not need to worry about here. What will be second? This is also even function.
So it
Yeah,
will be an identity matrix, right?
D1E is just a number, 1, right? You are still with me, right? I mean, D1E is 1. So yeah, this is just a number. It's a pure and simple number. Remember the irreducible representation, only 1, nothing else.
I guess he's saying about D5.
Sir, it will be D2E, no?
Oh no, that's where I will have to come to. This is the reason why I am giving this example and I cannot leave in between, and I am continuing with our class. This is the point which I wanted to now actually say. So let me write it and then explain it and then give you another question where let's see if you are able to answer or not. This is next point which I am going to give. So let me just write down, and then you have a confusion. confusion is that said D1E, then it should be D2 or D1. And then this one, the last one should be D2 or D1. So that's what I am going to answer now. Yeah. So this is the space of even functions, right? I said that xi1 is even, xi2 is even, and xi3 is even. Right?
D2 is for odd functions.
Say it again.
So D2 is for odd function, na, you told in first and second case.
Yeah. Okay, I mean, you are going, you are actually understanding, but let me just finish it off and then you comment, because then I think that you are raising question. Although I understand that you have understood something. Let me just go back and explain what has happened. Remember that this space where we were having this A4 representation, this space was having phi AX and phi BX. What kind of function phi AX was and what kind of function phi BX was? Phi
Even
AX
and
was
odd.
even and phi B was odd.
Odd.
We have representation which are the irreducible representation both for even and odd function. The first element which is there in both the cases, I mean, if you are looking at it, then the first element corresponds to the phi A portion, which is our even function. So in both of the cases, it was D1E and D1P. The second one, which is again the diagonal one, this guy is odd function, right? So odd function will have this D2E and D2P going on to the second diagonal. So because the space was having even comma odd function, hence the space was made constructed out of D1E and D2E. So this guy representing even and this guy representing odd. This guy representing even and this guy representing odd, which is the general form of structure A1, which was nothing but even, and A2, which is odd. Now we have gone to a space where all three functions are nothing but the even functions. Xi1, Xi2, Xi3, all are even. That means that all the diagonal elements will be represented by only one representation, which is the even representation. So you are writing it like this: D1E, D1E plus D1E. In fact, this guy is written even in this manner, just like that. And you can see the same thing which is happening, D1P plus D1P plus D1P, which can be written as 3D1P. Right? So what we have done now, that our fundamental not fundamental, our irreducible representations are such that they can take care of depending on what kind of functions you are getting. If you are getting functions which are some functions of even and odd, you can always diagonalize it. So that's the idea. Let's just do something else. Okay, more example. And this time only you guys are going to tell me. I am not going to say anything, just to see if I have understood, if you guys have understood. So psi4, psi5, psi6, what will be the dimension in this? Three functions are there.
T.
So it will be dimension 3. Okay, good. Excellent. Now psi4 is even and psi5 and psi6, they are odd. So function, one of the function is even, the first one, and the rest two functions are odd. How will you write now your A6? Okay. D6E and D6P. So give me D6E first.
Sir, will it be D1E, D2E, D2E
So
along diagonal?
D1E,
D2
D2E,
and D2E
E2E.
D2E along diagonal. And what about
and rest
D?
0.
Okay, rest here. Okay, let me just
Sir,
put
it should
0.
be 4, 5, 6, no? Not 1, 1.
No, but there are only two irreducible representation, right? D1 and D2. Rest all are reducible.
Oh, okay, sir.
Yeah. So what about D6P?
D1P,
D1P,
D2P,
D2P and D2P. So if I want to write down as the direct sum, D1E plus D2E plus D2E, or simply D1E, since it's a direct sum, diagonals one, so twice of D2E. And you can do something here, D1P plus 2D2P, all are operators, or I can write down my A6 representation is nothing but A1 plus twice of A2. So you have cracked it correctly. This is what it is supposed to be, that it is just like once you know the functions, and now I can actually give you any size. I mean, psi 10, psi 5, 7, 7, 8, 9, 10 functions are odd and even, and so on and so forth. So what we have done in essence, that we have broken a reducible representation, which is the higher dimension representation, in terms of irreducible representations, which are the lower dimension representation. The lowest possible ones are the numbers, which is there in this case. And I have shown you that what we do in this case, in these cases, that means that higher dimension representations or reducible representations can be written as the direct sums of the irreducible representation. I will invite question at this point, but I will continue with this concept a little bit more in the next class also. Questions here, and I will wrap up my class after that. I'm pretty sure that you may have questions like this. For example, will it always be possible to get one into one number representation? Will irreducible representation be always one into one numbers, basically one dimensional numbers? Or in certain cases, no, it is not. That's one question which comes very right. I mean, this is a question. Can I always break down this? Is it always possible to diagonalize the matrix? Or in certain cases, no. So there I request, I mean, just one homework which I would like you to do. Did you do something about the block diagonal matrices in quantum mechanics?
No, sir.
Not yet, sir.
Not yet, sir.
No, if you haven't done yet, then you wouldn't be able to do it, because now I'm pretty sure that that portion is gone. It is only the part of the first one. When you were finding out the simultaneous eigen functions, at that time this is generally. Anyway, okay, let's. I will just give you the concept in my next class about that what representations can always be. I mean, I'll just give you something, some an idea. Will always be reduced to irreducible representations which are number. And then for others, you may need to keep on finding out. One thing which is there in this case, that both the matrices should be simultaneously diagonalized using that matrix which we found. If one of the matrix cannot be diagonalized using that matrix, then this diagonalization will not work for that matrix. And hence you cannot say that you have reduced your original group into a smaller section group. So I will take that as the fundamental next class first point. Okay, good.
Sir,
Yes.
sir, can you switch to the third case where you told that the function is not odd or not even? I want to ask something from there, sir.
Yeah, sure. I mean, you asked the question and I will, I'm going there. You asked the question.
Yes, sir, here. So when P is operated on phi x, then in first equation, we get odd function, right, sir? And in second, we get even function.
P is operated on phi x. Oh, P operated on phi x. So you
Yes,
get
sir.
phi minus x. What is the purpose of, what is the function of P operator? Function of P operator, whenever it acts on something, let's say it acts on x, then this will make it minus x, right?
Yes, sir.
And whenever it is going to act on minus x, it is going to give it back,
Right,
right?
sir.
So this will be minus of minus x, which is phi x. So this is what I have written here, right? And then I can write down, of course, in terms of the basis functions, as the way we used to write down our operator. How did we used to figure out the matrix representation of an operator? By operating that operator on all the basis functions and then writing a matrix from that, right? Yes, no?
Yes, sir. Yes, sir.
Okay, now ask the question. Okay, go ahead.
Sir, so I'm just asking that when P is operated on 5x, then
We
we
get
get
5
5,
minus x.
then we get 5 minus x, then further
Right.
we rewrite it in
Zero.
basis.
In terms of the basis functions, which is 5x and 5 minus x, yes.
Sir,
Yes.
here we are getting odd function or even function that of 5x.
I mean, this is only 5 minus x. Where is the odd and even here coming? There is no odd and even coming here. You do not know anything about 5x. You do not know anything about 5 minus x. The basis function does not have that property, the symmetry, which you can enjoy here. It is only when you diagonalize it, then you will enjoy that symmetry in phi A and phi B, right? That is the reason of diagonalization. I mean, this is what we did. But here, phi x and phi minus I do not know what is whether they are even or odd, because they were never decided to be even or odd in the first place. I seem to be missing your confusion, to be honest. What is the confusion which you would like to raise? That then I would like to answer. Here I have done a very simple thing. I operated my operator on first basis function. I write it in terms of my basis functions. Then I operated my operator on the second basis function, and then I write that as the expansion so that I can write down the matrix representation of my operator. That's all I have done.
So here we have two functions, phi of x and phi of
Phi
minus
of
x,
minus x, right?
that is being operated by the two operators E and
One
P.
is E operator and another is P operator.
Yes, sir. So I was thinking that when E is operated on phi x, then it gives
Oh,
say
see,
P.
identity से मत confuse हो, because identity was still keeping the identity of the function. You do not
So
know whether the function was even or odd, right?
let's take case of P, that P is operated on phi x and it gives first even, then in second time it gives even. I was thinking like something
Oh,
that.
no, 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 no. Now I get the confusion. Actually, the confusion should have come in this sense. If you want to ask question, I can rephrase your question. I can say it this way. Let me- When I was doing phi 1x or phi 2x only,
Yes,
you
sir.
would say that what was I doing, to be honest? Because generally the space has functions which are, I mean, we cannot categorize at even or odd. But what I wanted to do, I just wanted to build my irreducible representations. Yeah. So that is why I started by saying, let's consider the function phi 1x. If you operate E and P on phi 1x, you get phi 1x only. That means that the basis function in the first state, which is one first case, is consisting of only one kind of functions, which are nothing but the even functions. You do not need two functions here. Both E and P have simultaneous eigenfunction in terms of phi 1x. That is what we did in this case. And we did the same thing for the second case. Both E and P have phi 2x as their simultaneous eigenfunction also. So phi 2x is the only single basis function which is required in this case 1 and case 2. And hence the representation was turning out to be only a number. Why would I do that? Because ultimately I will show that every representation can be reduced to these two irreducible representation. This is the reason why I always start with 1 and 2 cases. And then the more generic cases, when you go for the higher dimension, for example, phi x, when it is not even nor odd, things like those, these things are becoming clear to you that it can be broken down. Not that I broke down my D3P directly into my original one. Please see that. I first diagonalized my D3P and then broken it down in terms of the direct sums of the irreducible. Yeah, so take some time to go through the lecture. Hear my lecture again in case if you would like to. But please see that what I have done, I have used your knowledge of your linear vector spaces to construct representations. But then I said towards the end, very interesting thing, that those representations which you are constructing at the higher dimensions, you do not need to worry too much about it if you know the fundamental building blocks which are your irreducible representation. So our quest in the group theory will be to always look for irreducible representation, because we will continue to figure out any higher order reducible representation from that.
Yes,
Okay,
sir.
at this point, yeah, I cannot say beyond that for the time being.
Sir, just the crux of my concern is that when phi x is not odd and not even also means it contains both the terms odd and even, then when p is being operated on
No,
phi
at
x,
this
it
point,
gives.
no. I mean, when this basis is considered, there is no even, no odd. Phi x, phi minus x are both the functions which are neither even nor odd. It's a basis which is mandatorily required if you have a space of operators E and P. E and P operators do not have any simultaneous eigenfunction. But if you consider phi x and phi minus x, then they will be able to form any basis for this space. That's what I am saying. This
Yes, sir.
basis will require two functions, both of which are neither even nor odd. Neither phi x is even or odd, nor phi minus x is either even or odd.
So we can't decide the eigenfunction of p and e individually, right, sir?
No, at this point, no. I mean, the whole point that your P is coming in terms of the non-diagonal matrix, that means that there is no even an eigen. There is no eigenfunction here. Had there been eigenfunctions, what kind of matrix representation it is? If there are eigenfunctions. If eigenfunctions become the basis, what kind of matrix we are expecting for an operator? A little bit slowly. Again, ask the same question. If eigenfunctions are the basis functions, what kind of matrix representation an operator will have?
So as first and case we did same as.
Yeah, so I mean, you will need to revise your concept of your linear vector space again. And what is that? Let me just do it now that you have asked. So eigenfunctions are the basis. A phi 1, if eigenfunctions are the basis, lambda phi 1, right? A phi 2, lambda 2 phi 2, right?
Yes,
A phi
right.
n, lambda n phi n. And if I now see if there is a basis of phi I, which is nothing but the eigenfunctions, what kind of operator representation I have for this matrix? Tell me. First one, A phi 1, lambda 1 phi 1 plus how much phi 2?
So in first case all are zero except phi one.
So which means lambda 1 will come here, yeah, and
Yes, sir.
all are 0. And in the
Zero,
second
sir.
case, you will start with 0 and then
Lambda two.
lambda 2 and then 0 0 0 and
Zero, zero.
then what kind of
Right.
matrix are you getting?
Diagonal.
Diagonal matrix. This is the starting point of the lecture which I started with, that in case if you can find out that the eigenfunctions form the basis, then in that basis your operator will be represented by a diagonal matrix. Not only that, the elements of the diagonal matrices, they are nothing but the eigenvalues of that, right? In any other basis, so if I transform it to some other basis, which is I, let's say, which is not eigenfunctions of this, in any other basis of the same space, you will get S prime, which is having entries, non-zero entries here also, right? Those matrices are same as this matrix which is original one. And how do you reach from this non-diagonal matrix to diagonal matrix? How did you reach there? You do P inverse A P kind of
P.
operation, and this
Right.
diagonalized your matrix and you use to construct your P matrix. Yeah,
Yes, sir.
this is exactly what we have done here. To be honest, I took the longer route and I have done exactly that. First, I considered those functions. Now that you have asked it and I'm answering it, first I considered those functions. Okay, I'll have to stop somewhere here. So first I considered those functions which are not the eigenfunctions of both E and P. Phi x and phi minus x are eigenfunctions of E operator, but they are not the eigenfunctions of P operator. So they are not the eigenfunctions of the P operator, right? And
Right, sir.
then I considered A4. So this is my A4, where I took it to the place where now I have written in terms of phi x and phi bx. What is the purpose of writing this there? That if you operate P operator on phi ax, you are always going to get phi x. If you are going to operate P of phi bx, you are always going to get
minus
minus
5.
5x,
That's
which means that now phi a and phi b x, they are the eigenfunctions of p operator, and anyway they are the eigenfunction of identity operator all the time, because identity operator is like identity operator. Yeah. So
that's
that means that we did our similarity transformation to basically reach there. I gave you like this, but you could have done it in a very simple manner. You would have just diagonalized this second operator, this 0p, this guy, which I wrote. So had you diagonalized it here itself, without even looking for what kind of a space of wave functions it is, then you would have got the result for A4, except that you would not have known what kind of wave functions we are talking about. What the kind of wave functions we are talking about, they are the even and the odd wave function. So when we diagonalize a matrix, we always reach to the point where, so in this space we have A4, we always reach to the point where now whatever functions I must have given you to begin with should be the eigen functions of both the operator E and operator P. Then only the structure will become diagonal. Good point.
right, sir. Right, sir.
Okay. Okay. Yeah, I can understand the confusion because it is coming all from the linear vector space and we did it as the first topic. So maybe what you are suggesting is we should take that as the second topic after unit 1 if we want to do group theory, so that that remains fresh in your minds.
Right,
Yeah.
sir.
Yeah. That is the takeaway homework for the teacher.
You're right, sir.
Yeah, Ajay, but let me tell you one more thing, which will be another takeaway, and I can tell you that is also interesting. Whenever I start with group theory, the attendance falls down if the examination type is open book examination. Can you tell me the reason?
What, sir? I didn't hear you properly. Can you
Whenever
explain
I
that?
start, whenever I start group theory, this portion, group theory and representation theory, the attendance falls down in my online classes, particularly if the examination pattern is open book examination. Three things said together in a single sentence.
Cause, sir, it is OBE online.
Yeah, so with this, I had to tell you, I mean, the amount of cheating or unfair means which I have seen in your internal assessment, that's humongous. Not about any particular student, but in general, you are only few students left. We are going to, of course, come up with our internal assessment results soon. We have deducted, I mean, marginal numbers on the basis of unfair means. And once we open our internal assessment result, and if you come back to us saying, sir, we should have got full marks, and if we show it back to you that you have used unfair mean, whether you were the first who started with that, that means you wrote it and then you sent it to others, or somebody else wrote it and you sent it and you get it. In both the cases, I am going to give you 0 marks on that case. So we haven't given 0 marks currently for the unfair means, which is humongous. Humongous means humongous. You just look at the copies and you will say that, sir, I can tell you, you do not need to tell me that these copies are all basically replica of each other. Yeah, so it's a sad state, and that's where the problem comes.